the class. This will be section 12.3, dealing with the scalar product, which is often called the dot product. So those might be used interchangeably, talking scalar product or dot product. So we have to get back into the idea of what a scalar is again. So a scalar is just a quantity that has size but no direction. Okay, so it's distance, speed. If there's no direction, then it is not a vector. Okay, this will just end up being a number. So when we do our scalar product or our dot product, we get a number and not a new vector. So the formal definition, scalar product of two vectors is found by multiplying the coefficients of I together, the coefficients of j together, and the coefficients of k together, and then adding all of those up. So you're only going to look at the coefficients on the i's. We're going to multiply those, get a number. The coefficients on j, multiply those, get a number. The coefficients on k, multiply those, get a number. All three numbers added up will be the dot product or the scalar product. Written in vector form. So if we had some vector a and the coefficient on I was just a sub 1, the coefficient on j was a sub 2. Same thing for vector b. The dot product, and this is the notation for dot product, is simply going to be a1 times b1, because those are the coefficients on I, plus a2 times b2, because those are coefficients on j. We're going to add those together. Same idea if it was a three-dimensional vector and we had some k as a direction piece, then we would take the coefficients on k, multiply those together, and add this to the product. Also, now we can find angles between vectors. All right, so the scalar product is, so this dot product is the same thing as the magnitude of A times the magnitude of B times the angle between them. Okay, so again, theta is that angle between the vectors. So now we have a couple unknowns that we can move around and to solve for potentially the angle, or we could, if we're given an angle, we can find a magnitude. We can do all different things with it, but this relationship that the dot product is the magnitudes multiplied together times cosine of the angle between those two vectors. So let's look at one. Find the angle in degrees between vector A and vector B, given that A is 3i plus 4j, B is 5i plus 12j. And I specified in degrees. When working with vectors, we're going to be in degrees. Unless they specifically say something about radians, this one we will assume we're always in degrees when dealing with vectors. Okay, so first off, we know that that dot product is going to be our vector A times vector B, and we can find that by doing the magnitude of A times the magnitude of vector B times cosine of theta. All right, well, first off, let's figure out what this dot product is. So in the dot product, we're going to look at the variables I in those coefficients. So 3 times 5, so that gets us 15, plus 4 times 12. When we work that out, we end up with 48. So therefore, our dot product is 63. So now I know 63 is equal to the magnitude of A times the magnitude of B cosine of theta. And we're trying to figure out what that theta is. Well, we know we can find the magnitudes of A. The magnitude of A is going to be 3 squared plus 4 squared. That gets us square root of 25, which is just 5. Magnitude of B is going to end up being square root 5 squared plus 12 squared, square root of 169, which is 13. So now we have 63 equals 5 times 13 cosine of theta. 5 times 13, that's 65 cosine of theta. So therefore, 63 divided by 65 equals cosine of theta. So we're trying to figure out that angle. To solve for that angle, we're going to use inverse cosine of 63 over 65. That will get us theta. Work all that out. Ends up being 14.25 degrees. So again, this initial relationship here, this new formula we have to work with, we figure out what pieces we know and what pieces we don't know, solve for the unknown, it gets us to the answer. Now some special properties of the scalar product. If I had perpendicular vectors, so say I had some vector going this way, and then I have another vector coming off of it looking that way. If vectors are perpendicular, I know that angle between them has to be a right angle. And so this ends up being cosine of 90 degrees. If we think of our unit circle, cosine of 90 degrees, that puts us 90 degrees is right there at the top of our unit circle. Cosine is the x value. This all becomes 0. So it doesn't matter what my magnitudes of A and B are. I'm going to be multiplying by 0. So this all equals 0. So therefore, the dot product of perpendicular vectors is 0. If we have parallel vectors, so say we have a vector going this direction, then we have another one that can be smaller, okay, and they're scalar multiples of each other, but they are parallel if they are scalar multiples of each other. So we have two vectors going on. Now I will not have any angle between them. So it's cosine at 0 degrees. If I think of my unit circle, that puts me right here. Cosine of 0 degrees is 1. So the x coordinate there is 1. And so I'm taking the magnitude of A times the magnitude of B times 1. So therefore, the dot product of the two is going to be the same as the magnitudes multiplied by each other. Last one, coincident vectors. So coincident vectors are just two vectors that lie exactly on top of each other. All right, so say we had vector A times vector A, our dot product. The magnitude of A times the magnitude of A. Cosine of 0 degrees, it's not going to be on top. They're going to be directly on top of each other, so there's no angle between them. So that's simply our dot product is going to be equal to the magnitude of each, and we can simplify that to just being A squared. Okay, so practice problems. This 12, page 428, 3 ABC, and then these additional ones, these dot product ones go very quickly. So you shouldn't have a problem working through these. Even with my announcement that testing is kind of up in the air, we'll have an update on the 27th. Still want to work through all these vector problems. So keep putting in the work, look at my solutions, and we'll keep working through these vectors, and then we'll determine from there what the next course of action will be. As always, email me if you have any questions.